All right, so you said we already wrote. Would be a linked list. Okay, I gotcha. So we need to do it. Remove end and remove end index, and we currently, our implementation does not have tail, correct? All right, good, because I think you brought up that sometimes a tail node is also used to keep track of the beginning and the end of the list. A tail can be helpful even in singly linked lists just to keep track of the end, but really where it becomes very helpful is in doubly linked lists where you get to the end of the list and then you can actually traverse the list backwards. So every node then has a next node and a previous node. So just kind of maybe keep that in mind. It's not a drastically difficult thing to add. It just makes each of these remove at and end and add at one's a little bit more difficult because then you have to set up, connect up the previous nodes as well as you're patching everything back together. All right, so remove end. Let's draw our picture here. So we already, that guy, I'll just delete that guy. All right, so this is our list. So we want to remove this guy. And what does it mean to remove this guy? Well, it means go to the node immediately preceding him, correct? And but ultimately, we do want to return that guy. I think we did that for remove front. So we're returning the payload of that guy. So we need two things. We need to get to the guy immediately preceding him because we're ultimately going to want to set his next node to null. But before we do that, we want to preserve his next node so that we have the pointer to the node that we need to get the payload from. All right. So in order to get to the node whose next node is null, that's effectively what we want here, right? So walk our list until we hit a node whose next node, well, we do have a special case where we have the one list, correct? If that's the case, then we know head points to it. Otherwise, we have at least two things in the list, which means if this was the last thing in the list, we would go just get to there. That is the guy whose next node's next node is null. So let's write that piece. And we do have a count. So if self.count, and by the way, in remove front, did I decrement count? No. So we almost wrote remove front. All right, so if we actually remove a value from the list, our list does have one less value in it. So we need to make sure we update the value of count whenever we remove stuff. All right. So we'll steal some of this logic. So we don't try to remove end. So if count is equal to 0, hey, can't remove from the empty list. Great. Else if this dot count is equal to 1, if we only have one element in the list, we'll go ahead and say we're returning a string, right? String val to return is equal to this dot head dot get payload. And we'll say this dot head is equal to null. Then return val to return. Val to return. All right, so if it's the one list, we're ultimately going to make head point nowhere, and we'll let automatic garbage collection go ahead and clean up that node that used to point to. But we need to preserve its value before we do that so that we can ultimately return that value. And we've decided we're returning strings rather than nodes. So that's why we pulled the actual payload out of that node before we return it. Make sense? All right, so these are the two easy cases. Then, else, we must have a toList, minimum, toList or more, right? So we want to start at the beginning of the list and keep going until the cur node's next node is equal to null. We want to position ourselves right before. All right, so we'll go ahead and say node, cur node, and set this guy equal to this dot head, pointing at the beginning of the list because we don't want to change the value of head. It's actually kind of a common mistake that programmers make when they're first implementing linked lists, is they start messing around with the value of head, and next thing you know, they've lost the beginning of their list. So if you find yourself changing the value of the node of head, question yourself as to whether it's the correct time to be doing that. All right, so cur node is equal to this dot head, then we'll say while cur node dot get next node dot get next node is not equal to null. Cur node is equal to cur node dot get next node. So this will sprint us down our list, right? Updating cur node until we finally get to a cur node whose next node has a next node that is equal to null. So when we get here, we are one node short of the end of the list. That make sense? All right, then we can do our string val to return is equal to cur node dot get next node dot get payload. Then we'll set cur node dot set next node equal to null. So that's where we severed the connection, right? So we grab the value of the next guy, then we cut them off, and we're going to let automatic garbage collection clean them up, I guess, from memory. And then we'll ultimately return val to return. Does that look good for remove end? I mean, I might be testing you. I've never introduced a bug into my code, so it's... Let's find out if I was testing you. Let's just return -1 down there so this thing will compile. Oh.
I don't know if you checked my account.
I didn't. See, I was testing you. Ah! All right, so we'll probably could have written this so we only had one return statement, but whatever. So this dot count minus minus. All right, anybody catch any of my other tests? So let's find out if you're right. All right, so we'll go in here. We're adding A, B, C, whatever. Just want to see what's in that. What's that guy? Is that that's the I must still be running. It's my step thing. All right, so there's my current list, and we did remove end last time, but now remove end, or we did remove front last time, but now remove front should accurately update count now. All right, so now we're going to go ahead and we will print out remove end. Hello. Hello.
It sure is great to get into this map.
What's up?
Why is the run what's there again before this line?
Okay. So A, B, C at 0, 1, 2. Then we added D at the end.
Oh yeah.
And then we added E at 3.
Makes sense. Okay.
Okay.
It was just
Yeah.
the alphabet was broken. So.
Oh yeah. I do that. Yeah. I have a strong disagreement with the actual alphabet. I think some of those letters are in poor places. All right, so we'll remove N now, and then we'll display again. And what was at the end? D?
Yeah.
All right, so there's our D. We removed it from the end. I mean, we can test the one list. I don't think it's really that necessary, but whatever, we'll do it. So this should still do the A points to null. There's the end. Now we have the empty list. We'll go ahead and we'll test the empty list, and we should get our runtime exception. Hey, can't remove from the empty list, blah, blah, blah. Okay, so that guy looks like he's doing what he's supposed to do. And that should be, remove n should have been the easier of the two methods you had to write. All the things at indexes are always the more difficult because we have to kind of surgically piece things back together, right? All right, so let's look at remove at index. And let's go ahead and take care of our trivial cases first. So we'll do our if count is equal to 0 stuff. Can't remove stuff from from the empty list. Else if index is less than 0 or index is greater than this dot count. This dot count is the number of elements, so the last legal one would be, so it's greater than this dot count minus 1, right? Or greater than or equal to this dot count. And that just has to do with how we keep track of count. I think we're treating it like strings and arrays. So it's 0 to count minus 1 as the legal buckets. Okay. Then we'll throw another runtime exception. Okay, bad index. Good enough. I mean, if we want to show them the index that they gave us, we can tack that on to the end there. All right, else if this dot count is equal to 1, what might we do in the situation where this dot count is equal to 1? Call remove front or call remove end. Either one would get the job done. So we'll go ahead and return this dot remove front. Now we could have done something similar in that if statement for remove end. All right, so if it's the one list, let's not reinvent the wheel. We'll just go ahead and use our remove front to remove the one element that's there. And remember, we're only kicking here if it wasn't the empty list and they gave us a legitimate index. All right, so if we're here and we have a count of 1, the index they gave us must have been 0. All right. Else, we're here, we have a legitimate index and we have at least a 2 list. We have a legit index and at least a 2 list. Minder options. Very exciting. All right. So if that's the case, let's go look at our picture for this guy. Now, we have a trivial case here where if they said remove, or if index is 0, we can remove front, right? So we can actually update this where if this dot count is equal to 1 or index is equal to 0. If either of those is true, we'll go ahead and remove front. Does that make sense? We can have this if statement, you play double duty. So you gave me a legal index. If the count is 1, that index must have been 0. Or if the index is equal to 0, we can do this. Now, we could also say just index equivalent to 0, and that says the same thing. So we didn't actually have to confirm it was a 1 list. Okay, so if you prefer seeing it like that, where we're explicitly saying the cases that we're handling there, that's fine. One extra question you're asking, not the end of the world. Linked lists are already slow. All right. But technically, index equals 0 is good enough there, because if we get to this point here, we know we're dealing with a legitimate index. So we can go ahead and handle index 0. If it's anything other than index 0, then we know we have a legitimate index and we have at least a to list. All right, so if it was bucket 1, for example, so if index is equal to 1, this is the guy we want to remove. Okay? Now, in order to remove him, we might, we really could handle a one other special case here. That's what if it's the last legal bucket. That'll make life easier as well to do this stitching up thing. So the last legal bucket is if index is equal to count minus 1, right? So else if index is equal to this dot count minus 1, we'll go ahead and return remove end. So we're just passing the buck. We'll call remove end. Remove end is going to give us the payload it finished removing, and we'll just return that payload. All right. Else, we have a legit index, at least a to list, and index is not the front or end. That's the situation we're in if we're in that else. Okay? So now we come in here, so we know we're dealing with something like an E or a C for the value we're returning here in our example here. We're not dealing with the extremities. Oh, I like that word. Oh, I did find, well, I gotta see if I can come up with it here. I found the new emoji. That looks just like the ones my wife hates too. I texted that to her last night. Didn't go over well. All right. So in order to remove this guy, we ultimately are going to have the dude before him point to the same place he points to. And then we need to disconnect who he points to, right? All without losing track of any nodes. All right, so since we need to get to the dude before him, we probably want to go ahead and create the variable dude before him, right? And that's going to run our list. So if this is bucket 1, we're going to have a for loop that's going to start at the beginning of the list, go through one time, going from head to the next node. Okay, historically we've called this cur node, but I like the dude before him variable name. So we'll say node dude before him is equal to this dot head for int I is equal to 0, I is less than index, I plus plus, dude before him, oh, I regret this variable name because I can't spell this, is equal to dude before him dot get next node. All right, so at the end of that for loop, we've positioned dude before him to point to the node preceding the guy we're actually going to remove. Okay? Now, we can go ahead if we want to give ourselves a variable for the guy we're actually going to remove. Oh, come on. I'm better at copying than that. Nailed it. Guy to remove. I'm not better at copying than that. You can't do it too quickly. All right, so we'll have this guy point at the next guy. So we'll go ahead and give ourselves a node guy to remove is equal to dude before him dot get next node. All right, so we have both of those pointers. Now we can say dude before him dot set next node equal to guy to remove dot get next node. Make sense? So dude before him dot set next node equal to guy to remove dot get next node. All right, so that line right there does this. Okay. Last thing, well, second to last thing, I guess, we need to disconnect this guy. It actually would not be absolutely required because when this method ends, guy to remove would be the only one pointing here, so this guy would get reclaimed. But for completeness, I typically like releasing all the pointers, so I would set this guy to point to null. So guy to remove dot set next node to null. Fully disconnect the node. Otherwise, you're kind of relying on the behavior of automatic garbage collection, which it would do what we want it to do in this case, but let's not trust that. So we'll say guy to remove dot set next node to null. So that does this. Then finally, we want to return guy to remove dot get payload. Make sense? So we've extracted that E, we returned that value, and everybody's happy. Now we need to make sure we update our count. Now, another common mistake here, we will not update our count here or here because remove front and remove end update our count for us. So be careful not to double update, right? Don't decrement count twice in the event that you're relying on one of your other tools to do the removal. But down here, we did the removal. So before we actually return the final value here, we'll go ahead and say this dot count minus minus to decrement that guy. And I think that's the only count we're responsible for. That's where we actually did the surgery. Okay, so I think that should be remove at index. Let's go ahead and test that dude. All right, so we added E at 3, good, and then we'll remove at index 3. So that'll get rid of the E, right? And then we'll display it again. So we should have a list with E, then a list without E. Here's the remove at index 3. Repro. 0, 1, 2. Oh, that is at bucket 3. No, it's not. 0, 1, 2, 3. So the E is at bucket 3, but we're actually removing the guy after that. So if I said 3, does my loop say less than?
It does does, but then it's getting the next node.
What are you all dressed up for? It's not becoming. Almost didn't recognize him. Okay, so we're going through too many times here. So if I say 3, so you want to say less than index minus 1, that'll fix it, but let's just make sure we're following this. So we'll start at 0. If index was 3, we'll say, so is 0 less than, let's just see it go through the extra time. Is 0 less than 3? Yes, it is. So now dude before him points to bucket 1. I becomes 1. Is 1 less than 3? Yes, it is. Dude before him points to bucket 2. So I less than, then I becomes 2. Is 2 less than 3? Yes, it is. Now it points to bucket 3. Is, so 0. Then it's 1. And this guy points to 1. So that last time through, when he was 3, now he's 4. CD. This is 3. Starts at bucket 0. Now it's bucket 1. This is 1. Now it's bucket 2. This is 2. Oh, we want this guy to always be the dude before him, so we could start this off at 1 if we wanted to. That should have been less than index minus 1 anyways. Zero, 1, 2, 3. I'm displaying it. Then we're removing bucket 3. So that's going to get into this else here. Start at the beginning. This is going to go through, it's 3, 1, 2, this will go through twice. So the first time, dude before him goes from here to here. The second time, dude before him goes from here to here. So I think dude before him is pointing to the correct place here. Then guy to remove is dude before him dot get next node, which should be this guy. Then we say guy to remove dot set next node. Do before him set next node to get next node. So this guy now points to this guy. Why is it seems very strange. Zero, 1, 2, 3, 4. Okay. Remove at index 3 is going to come in here. So let's watch him traverse. So this should start at the beginning, print out as dude before him is moving. so that when we finally get to here, let's see it again. So the last time we see that, so the second to last line before the printout should be the last position of dude before him. Oh, we're not getting into that code. So that means, oh, this is the problem. Index is equal to count. So the count here is 2, 3, 4, 5. So there's 5 elements here. This is 0 to 4. If I say remove 4, then that goes to, all right, somebody's not incrementing his count. That's the bug. So let's look at our ads. And we can prove that real quick. I'm thinking that I'll just make that public for a second. So that's going to be 4 instead of 5, I believe. Yep. All right. Who's not incrementing their count? Let's look at our ads. All right. Added index. He's not incrementing his count. I guess we could just do it at the end, but it doesn't matter. All right. There we go. Let's make this private again. Oh, that's our printout. So A, B, C. The very last place it's pointing to right now is E, which is the one too many, right? So let's run that again. So here's the first place dude before him points to. That's the same as head. Then it points to B, still in the loop. Then it points to C, still in the loop. And that's really where we want it to end. But it ends up finally pointing at E. So it's actually minus 2. I'm printing out dude before him right here.
No, because you're printing out the E when you delete it. That's where the E's come from.
Oh, so that dude before him was the last. Yeah, I got you. Yeah, it's so this was the dude before him, which was C. So that's the right position. This is the value that we did remove, and this is the list after it was removed.
Right.
All right. You passed the test. Okay. So we were going through this an extra time. So we can either leave this at 0 and do index -1 or go 1 to index. But the bigger bug, problematic bug, was we were not decrementing or incrementing our count when we added stuff. All right. So let me go ahead and, do you want me to paste the whole thing or just the two new methods? All right. Well, let's do the whole thing since we updated that count. Yeah. All right. Then we're going to talk about the stack data structure. So 2, 21, 17. Homework solution. All right. So now let's talk about stacks. I mean, what we've written here so far is a singly linked list. We may end up through one of our other implementations making it a doubly linked list, but I think the jump to a doubly linked list isn't this crazy thing, right? It means that every node not only has a next node, it also has a previous node. So as we're hooking stuff up, we just need to draw more pictures to make sure that we hook the extra nodes up as we are disconnecting stuff. All right, so it's just more of the same exercises we've been doing. All right, so now if you remember back when I first introduced this, we talked about linear linked data structures. All right, so a linked list is our first example of a linear linked data structure. So that means in a line. Okay, now we've looked at a generic plain Jane linked list and saw we've written kind of a generic one, right? That can do all sorts of stuff. We can get at a position, we can add front, add end, add an index, remove front, remove end, remove an index. We can do all sorts of things, right? Now, that's a very general purpose linked list that we can use to solve all sorts of problems. Well, we have a data structure known as a stack. All right, now a stack is we're going to say it's a special implementation of a linear linked data structure, in this case a linked list. Okay, stack has 3 functions. Really, 2 functions are official functions of a stack. The other one is one of those nice to have functions that pretty much everybody writes. All right, so stack we have push, pop, and peek. Okay, so push, and when we think about our stack, think of it like a stack of magazines. All right, so a stack is a last in, first out data structure. So when you have a stack of magazines and you add a new magazine to that stack, you're putting that on top. When you remove an element from that stack, you're removing the top. So we push a magazine onto the top of the stack, we pop the magazine off the top of the stack. That makes sense? Now, peek lets us see the top of the stack without actually removing it. Make sense? So push says add to the top of the stack. Pop says remove from the top of the stack. Peek says get from the top of the stack. All right.
Push S to the front of it.
Say this again. Well, effectively front or end, depending on how you decide you're going to implement your stack. End would be a very poor choice. In this case, since we have a singly linked list, end could work, but wouldn't be the smartest way of doing it. So should be the front. So let's go ahead and implement our stack. Now, what you will find some languages do is they build those functions into linked list. Now, really what we should be doing is we should be abstracting linked list and creating a special version of it, right? So we're going to go ahead, we're going to create a new file here called stack.java. Is this us? Nope. Spring. Is this us? All right, so we'll create a new class called stack. And we're going to say that stack extends linked list. Okay, so that guy gets everything that a linked list gets initially. All right. Now, what we're going to do here is we're going to implement our couple of functions. So we're going to have a public string. We'll do public void push first. Then we'll have public string pop. And we'll have public string peek. Okay. Now, push says that's effectively what? This dot, and we need to have this guy taken out. String payload. This dot add front payload. Pop is return this dot remove front. Pop is return this dot get at index 0. Does that make sense? All right, so that's the entire stack data structure implemented in terms of a linked list. Now, it just so happens that our stack data structure, because it's implemented in terms of a linked list, is going to come with some additional functionality that we could choose to use, like get count and all that stuff. Okay, it comes with it. Now, we certainly could have re-implemented these things ourselves. The nice thing is if you had to write a stack from scratch, it's far simpler than writing a linked list, correct? So, I mean, this is an accurate stack data structure as we have it written, but it's written in terms of a linked list and it can do more than the typical stack. But let's say you needed to use a stack in one of your, in a project. You didn't already have your linked list available to you and you weren't using one of the built-in libraries that give you linked lists or stacks or any of those guys. So if we were going to write our own version of it, just so we're using the right lingo of the top and all that stuff, we would go ahead, we would say, private node top. We would say this guy no longer extends linked list. He's his own entity. Okay. So stack. We'd have our constructor for this guy, public stack. We say this dot top is equal to null, and it probably wouldn't hurt to go ahead and keep track of a count as well. We could spell that a little bit better, I think. Okay. Now, when we push, what we're going to be doing is we're going to be making head point to this new guy. Remember how easy add front was to write? Not an overly difficult thing. So we'll say if this dot top is equal to null, then we'll say this dot top is equal to a new node built out of our payload. Else, actually, I guess we could just create our node end up. Else, node.setNextNode will be equal to this dot top, and then this dot top is equal to n. And in either case, count just got a little bit bigger. So when we push something, what do? We create a new payload, or create a new node given the payload that was passed in. If we're currently dealing with the empty stack, we go ahead and we just set the top of the stack equal to the new dude. If we're not dealing with the empty stack, we set the new dude's next node equal to the same place that is currently the top of the stack. Then we update the top of the stack. Make sense? And we also increment count. What about pop? Well, pop is the same thing as remove front from before. So if this dot top is equal to null, meaning we don't have anything at the top of the stack, then we'll throw a new runtime exception, can't pop from the empty stack. Else, we have something real, okay? So we'll go ahead and we'll get our, to match up to our other implementation, we'll go ahead and we'll say string val to return is equal to this dot top dot get payload. Then we'll say this dot top is equal to this dot top dot get next node. Then we'll return val to return. And before we do that, we need to make sure we say this dot count minus minus. We have one less thing than we used to have. So that's pop. Now, peek is similar to pop, with the exception of we don't actually remove it. All right, so I'll steal all this code. You could actually implement peek in terms of pop. You can go ahead and pop the top of the stack off, store the value you want to return that was in there, and then push it back onto the stack before you return it. Right? It's like, oh, see, that's the pop noise. Okay, I have the value. I'm going to put it in a little variable here to return, and I'll go ahead and put them back on. I don't have the put back on noise. All right, but we'll go ahead and just implement it directly. So peek, if top is equal to null, empty stack, nothing to peek, something like that. Otherwise, we'll go ahead and get the value we're going to return, but we're not going to update top. We're not going to return, or not going to change count. So really, we're actually just going to return the payload of top without modifying top. That makes sense? All right. Now, so here's a fun one. So it's I guess an in-class challenge. It's helpful to be able to display any of our linked data structures, correct? That way we can kind of test to make sure they're working. So we're going to have our public void display for our stack. Now, even though we know that stacks are effectively linked lists. We need to write display in terms of the stack functions. So we can't do our, we're only allowed to manipulate the stack using his own functions. We're not allowed to do our little traversal where we walk from top to the node that has no next node and print out each one. We actually have to use the stack functions to pull this off. So how would display work? Let's draw our little picture here. I'll steal one of these dudes. Okay, so even though we know there's some next nodes in there, our stack visually looks like that. And we have a variable called top. Well, I wonder, do I get a... Nope. Let's see if I got an emoji for top. Oh, big top. Circus. No. Terrible. All right, so top points to the top of the stack. Now I want to display this stack in terms of its own functions without destroying my stack. So any destruction that I might do, I need to make sure I put things back the way they were when I'm done. How would I do that?
Destroy it, make a new stack along with it. And so like you read off that you pop and then push it back to a new stack.
Okay. So if I pop this guy off of here, and then you want to push him onto another stack.
Yeah, but in the process you read what's in that as you're pushing.
And print it?
Yeah.
Okay. So I just printed A, right? So there's my A. We'll just deal with the capitalization. Then you want to pop again.
Right.
And push.
Flip it over.
There's my B. Then you want to pop again and push. There's my C.
You have to pop and push them all back on the original.
Yeah, and you have to pop it back.
Oh, is that a problem? Yeah, so this was a temporary stack, right?
Right.
So you created a secondary stack. You popped everything off the first stack until its count was 0. Pushed it onto the new stack. Then you're going to pop off the new stack, pushing it onto the old stack. All right. And you're going to do that until its count is 0, correct? But wait a minute. Count is private. So if I create a stack called temp is equal to a new stack, when I go to pop, so we can access our count locally, right? So I can say for int I is equal to 0, I is less than this dot count, I plus plus. We'll go ahead and we'll do a system dot out dot print this dot peak. And then maybe concatenate onto that. I don't know, we'll do our little arrow thing, something like that. Then we'll do temp dot push this dot pop. Right? And so we're printing along the way. Then if we want to make it look like the last thing we did, we would do a system.out.println. I think we had it go to null, right? Showing that's the end of the linked data structure, if you will. Okay, well now we need to put everything back. How many times do we need to do it? We need to do it the count of temp. How do we access count of temp? I'm trying to trick you right now, by the way. Because temp is a different variable. Count is a private variable.
So if you access count, you'd be accessing the 0 count of temp right.
Maybe. I guess it depends how you access count. What you really want is temps count, right? But temps count is private. What does it mean for a variable to be private?
Only accessible from within its class.
Yeah, it's only accessible within this class, right? Specifically, a private variable count here is only accessible inside of a class called stack. Am I in a class called stack? I'm in a class called stack. So in this case, I'm allowed to say for int I is equal to 0, I is less than temp.count. I can access temp's count variable even though it's a private variable within temp. Since temp is a stack and I'm currently inside of the stack class, I have access to that private variable. Okay, it's like I'm allowed, right? I++. Now imagine some of the limitations you might have with private variables. I like using this example. Imagine limitations you would have with private variables if you couldn't do things like this. We have two stacks here. We have this, the stack we're currently working with, right? And then we have temp, this extra stack. And I happen to need to know the count of both of those guys at one time or another as we're going through here. But I really don't want count to be a public variable otherwise. So I don't want to just make it public so this works. I'd rather this just kind of work because it maybe makes sense for it to work. That makes sense? So the concept of making something private allows this type of thing to work. So it's a kind of a, I don't know, let's say it's a feature or a well thought out feature as opposed to Java removing structs, which was not a well thought out feature. So whatever. Okay, so now we need to go through and we need to pop everything off temp, pushing it back onto this. And at this point, this should be the empty stack, correct? So we'll say this dot push temp dot pop. So that puts the puzzle back together after we destroyed it. So we popped everything off the stack, display it, because I didn't let you use any of the other things. Then we pushed it all back on to make everything happy again. Okay. Now, this is what we do if we're not looking at the empty stack, right? Probably need to have our special case for the empty stack so we can just say empty stack. So we'll say if this dot count is equal to 0, system.out.println empty stack. Nailed it. Else this stuff. So if you didn't catch that bug, too many semicolons. I sometimes throw those things out there. Just never know. Okay, we're fixed now. So let's go out to driver. Let's dump this stuff. Let's create our stack. S is equal to a new stack. We'll go say s dot push, and we'll, since you were so concerned about the alphabet being correct, I'll adhere to your traditional alphabet. Okay, so we'll push on a C, then a B, then an A, so the alphabet's in order. Okay, but that's for you. You remember this. All right, so we'll push on the C. Then we'll push on, we're peeking. We'll push on the B. We will push on the A. Then we'll do s.display. Row. So we are not going through enough times. Or stick. Oh, this is a good one actually. All right. This is a obviously I put this bug in there on purpose. What's the problem with this one? Anybody see the bug?
Less than R.
No. Go ahead.
Should it be this count -1?
No, it's kind of the same thing he was saying. I think we're going through the correct number of times in theory. This is actually a common bug, which is why I obviously put it in there to show this to you. It's actually a problem. It's problematic with data structures like this. What am I doing inside this for loop? Just roughly speaking.
Is it because you're popping before you read it?
Well, no, I'm peeking first,
Okay.
and then I'm popping. There you go. There you go.
Count changes within
Every time I pop, count's changing. Okay, so I'm looping on count.
Uh-oh.
Does that make sense? Okay, so it's actually you'll get an exception when we eventually look at the built-in collection types in Java. We have a linked list and a stack. Those things exist in Java. If you probably could have guessed that before, right? We're writing our own right now, but we have these things in Java called iterators, which effectively is a for each loop for linked lists for these collection types. So I can say for each element in a linked list, do something, but you'll get screamed at in there if you change your linked list inside. Okay? Because what it does is the way the iterator is implemented is in terms of the number of elements in it. How can I fix this? I don't need to do much, but
Just store count in a different variable.
yeah, I just need to temporarily hold on to count in a variable that I'm not changing, right? Because in theory, I'm going through this .count number of times until I start changing count, right? So everything I'm doing is fine, except I'm it's like one of those things where I saw some YouTube video lately. Oh, I know what it was. Actually, it's kind of creepy. I thought about it. So there was this guy in a shower. I think it was at the beach. And so there's some guy just got out of the beach and he was like, rinsing off the salt water or whatever. And they had shampoo there. Well, so he was washing his hair and then rinsing it off. And while he was rinsing it off, when he would stand back up, some guy was like behind there and he put a little more shampoo. And the guy was driving himself crazy, just over and over again. It just wouldn't go away. I don't know why I thought about that, but well, sometimes people are creepy. So we'll just call this temp count, and this is this .count, and then we can use temp count in here. Like that. And then we're going to go ahead and we're going to reuse temp count again, because we're going to have a pretty similar issue down here as we are popping stuff off of temp while still using temps count. So we'll go ahead and actually store temps count inside of temp count. That makes sense? All right, now we can change the count inside of our list to our heart's content because we have it stored here and that's passed by value, which means there's no side effect. I get a copy of the original value of count stored inside of temp count, and changing count right here does not have an impact on temp count. So that's an example of pass by. Well, we're not passing it, but effectively the same thing as pass by value. with no side effect. All right, so let's test this dude again. So there's our ABC displayed. All right, and remember when I pushed it, I pushed the C on first, then I pushed the B on top of that, then I pushed the A on top of that. So it is the stack ABC, the traditional alphabet that Corey is such a huge fan of. Okay, I like to be a little bit more random. Okay, so questions about that. All right, now, how many of you have heard of the game Towers of Hanoi? Never heard of the game Towers of Hanoi?
Karsten told me that we're going to be writing this when I told him what we were doing in 300.
Now this is going to be the easy question because the one for next class is just worst parts of the Bible times 3 maybe, something like that. All right, so let's show you Towers of Hanoi. Actually, we can probably. Probably a sample thing. It's going to give me like a ha-ha. Okay, so this is Towers of Hanoi. All right. So I need to warn you, I'm an expert at this. I learned from the best. And Mr. Gonzalez has been playing this for years. All right. So the goal is you have 3 towers, 3 stacks. This is a stack. This is a stack. This is a stack. All right. The goal is you start off, in our version of the game, you only have 3 discs. And because as the game, you can challenge yourself by giving yourself more discs in this version of the game. But we're going to start off simple, and then we're going to write this as an Android app next. All right. But we'll start with text-based. If you want to challenge yourself and do it for Android right off the bat, that's fine. I don't care. But let's focus on stacks for one more class at least. The goal is to get all of these things from this first stack over to this last stack in the same order. But now there's a rule. The rule is that a larger disk can these are the disks. They can never go on top of a smaller disk. Okay? So that means if I can move this guy to either one of these stacks. Okay? So if I move him here, I am not allowed to move this guy here. That makes sense? That's an illegal move. So I can move him there. Then I can move him here, and that's allowed because that disk is smaller than the disk below him. Then I can move this guy here. Then I can move this guy here. Then I can move this guy here. And finally I can move that guy there. Okay, and that was in the minimum number of moves you can do doing this manually. Like I said, I'm a professional. All right. Yeah, I mean, there's this whole world circuit for this. I travel. I used to, before you had things like this, I used to bring, I think it was like, I don't know, from Hasbro or something. It was like these little kids' toys with little rings. Yeah. I would say that's my profession. That's the kit I travel with. I usually have to check it because TSA doesn't really trust it. It looks a little... All right, so for our homework, we're going to implement a text-based version of Towers of Hanoi. So you're going to have 3 stacks. Now, our nodes are probably not going to be strings. Probably want them to be numbers. If you want to leave them as strings, that's fine because we have that little tool, integer.parseInt, that can squeeze the number out of a string. So I'm giving you some hints here how you might implement this. Maybe you say that this guy has a payload of 1. This guy has a payload of 2. This guy has a payload of 3. That way you can do the check because these are conditional pushes, right? When you try to push, let me restart this. When I try to push this guy on top of this stack, it's not going to let me do this because the current top of that stack has a payload that's smaller than the node I'm trying to add. Not allowed. Okay? So it's a stack, but it's a conditional stack because it's a Tower of Hanoi. Make sense? All right, so and remember the way we do user input is through the scanner class. You want to just see a quick example in our final minute here. Scanner input is equal to new scanner system.in. So we'll just, here, I'll just say string blah is equal to input dot next. System.out.println, whatever we read in blah. And I'm not going to get a prompt here, but I'll still type stuff. It'll work out. So there's that. It's asking for some stuff. I'll type that in, and it spit it back to me. All right, so that's how we use the scanner to read stuff in. So what I would recommend is you'll initially show your 3 towers, and if you want, you can put them right on top of each other. You don't need to spend time making this beautiful text-based layout. All right, just display 3 stacks. All right, everybody's happy. I would then choose 2 numbers. The source stack, that is the stack I'm going to pop off of, and then the destination stack, the guy I'm going to push onto. That makes sense? The game is over once your last stack has all the guys on it in the original order. Make sense? So 1 player, all manual, you get to choose. So, make sense? Text-based, pick your poison, whatever. If you want to challenge yourself and do this for Android, you can, but this is good practice with stacks. So due for Thursday. Questions, comments, concerns, bribes? All right, and I'll give you a link to this guy so you can play Towers of Hanoi, and maybe one day you can beat me. All right, I'll see everybody on Thursday. Don't forget, today is student, faculty, staff Bible study. Just go down to the cafeteria, sign in, you get a free lunch, God and grub. Then we have a couple computer science tables. We sit down in the terrace room, but many of us meet for lunch right now at 11:30 in the caf and then walk down afterwards. So if you're interested, please come. You're all invited.
So I'm allowed to use ints now.
Finally, your time has come. You can use integers.
So the homework, you just